If you've ever tried scaling a reward model and thought, do I really need a 600B parameter beast for better alignment? DeepSeek has a sharp reply. Maybe just sample more and let your model vote. This paper introduces GRM, a pointwise generative reward model trained with self-principled critique tuning. Yep, SPCT. Instead of relying on static labels or handcrafted metrics, it generates its own principles and critiques on the fly. Then, by sampling multiple reward generations and aggregating via either voting or a meta RM, it achieves inference time gains that rival much larger models. In short, inference-time scaling finally gets a serious strategy for reward modeling, and it's not just about more flops. Let's break it down.
In the world of large language models, reinforcement learning is commonly used to fine-tune models after initial training. But there's a catch. It's not only about how much compute you use at training time. The authors argue that inference-time compute, meaning the compute used when the model makes predictions, can also drastically affect performance on reasoning-heavy tasks. That's the starting inspiration. There's also a major challenge in RL, getting accurate reward signals. When your tasks aren't strictly verifiable, like math or coding, it's tough to know what correct looks like. Existing reward models often rely on handcrafted rules or narrow domains. The paper aims to overcome these limits by building a more generalist reward model, which should handle diverse queries and also leverage more inference compute to refine its judgments. They approach this by proposing a generative reward modeling strategy. Instead of assigning a single numeric score, their model generates full-text critiques and describes the principles it's using. This approach is more flexible and sets the stage for what the authors call inference-time scaling, using multiple samples during inference to reach better outcomes. The method they introduce is called self-principled critique tuning, abbreviated as SPCT, where the model learns to generate both its own principles and its own critiques via online reinforcement learning. During inference, the model samples multiple critiques in parallel, then either votes or uses a separate meta-reward model to select the best judgment. Look at Figure 1 here. It illustrates how performance improves as you increase the number of samples. Their approach beats other models, even those with huge parameter counts like Nemotron, 340 billion parameters. The takeaway is that strategically sampling at inference can outperform just scaling up model size. They wrap this up in the abstract by saying that DeepSeek-ERM with SPCT, that stands for DeepSeek Generalist Reward Model, fine-tuned with self-principled critique tuning, not only improves performance, but also scales with inference compute. Sometimes, it can even outperform more expensive training time scaling. I admit there are still open challenges, but it's a promising step toward building generalist reward models. Let's look at why generalist reward modeling is such a hard problem. If you're only dealing with math or code, it's easier to verify correctness and handcraft reward signals. But in open-ended tasks, like creative writing or logical reasoning, there isn't always a single right answer. That uncertainty makes designing a universal reward model tough. Typically, reward models come in different forms. Some are scalar, assigning a numerical score to each response. Others are pairwise, comparing two responses and picking the better ones. And then there are generative models, which output a critique or reasoning process before assigning a score. Scalar models can be too simplistic for complex tasks. Pairwise models don't always scale well. Generative models are the most flexible, but need robust guidelines. This paper draws attention to inference-time scalability, using more compute at prediction time as a powerful way to boost performance. The question they pose: can we build a single method that lets a reward model benefit from more inference compute? They answer yes, and that's where self-principled critique tuning, SPCT, comes in. SPCT teaches a generative reward model to produce its own evaluation principles and critiques. The authors also introduce their DeepSeek-GRM27B model, fine-tuned with SPCT. At inference, it can sample multiple principles and critiques for a single response. Then it uses either voting or a specialized meta-model to combine them into a final reward. This leads to more nuanced judgments, particularly in tasks where multiple answers could be correct. This shifts the conversation from training time methods to inference time strategies. In other words, the model can think harder on the fly, rather than just relying on bigger parameter counts. Let's dig deeper into how these reward models are structured. The paper categorizes them by the way they generate rewards and how they score them. On the generation side, we have scalar models that just spit out a numeric score. Semi-scalar models might generate a brief critique alongside the score. Full-blown generative models write out a complete critique first, and from that critique, we extract the final score. On the scoring side, there's pointwise scoring, which rates each response individually, and pairwise scoring, which compares two responses at a time. If you check out Figure 2, you'll see how these different configurations line up. Some are simple but less flexible, like Bradley-Terry or PairRM. Others, like Cloud or a pointwise generative reward model, pointwise GRM, allow more freedom during inference. That freedom is critical if you want to improve performance without retraining. This is why they highlight generative, pointwise models as the sweet spot for inference-time scalability. It's the basis for SPCT, where the model learns to write detailed critiques that can be sampled extensively. The authors show that SPCT works not just for their own DeepSeek-GRM, but also scales up nicely for bigger language models. So the key insight here is that to get a reward model that can improve by thinking more at inference time, you need a generative approach that's pointwise, not locked into pairwise comparisons. That's where SPCT fits in. Now let's talk about how these generalist reward models get better at evaluating answers by using principles. If we want to scale up a model's reasoning at inference time by generating multiple samples or critiques, it can't just give the same score to every response. Scalar models can struggle with that. They often produce near-identical scores for different answers, missing subtle distinctions. The paper proposes a more structured approach. The model generates critiques and turns them into numerical scores. But how do we make sure the critiques aren't random? That's where principles come in. These are like mini rubrics that guide the evaluation. They can be either handcrafted or generated automatically. The authors generated some with GPT-4o and filtered out the noisy ones. Check out Table 1. It shows how filtered principles helped boost performance on benchmarks like ChetHard and IF-eval. Even self-generated principles gave a small improvement, but well-selected principles were more impactful. This sets the stage for self-principled critique tuning, SPCT. SPCT pushes models to create and use their own principles dynamically, rather than just following a fixed set of rules. It's a leap toward letting models not just critique, but also explain how they're critiquing, which makes them more adaptable and more powerful at inference time. The authors call this unpinning principles from understanding to generation. In simpler terms, they're not just coding in the rules. They're teaching the model to come up with the rules itself. So how does SPCT actually work? Picture this. Instead of hard-coding your model with evaluation rules, you train it to generate its own principles. Then it uses these principles to critique responses. Look at Figure 3 here. It gives you the big picture of how training and inference each operate. During offline training, the model is encouraged to output principles like be consistent with the query or base your reasoning on solid logic. Then use them to assess candidate responses. Each response is scored on how well it follows those principles. Some principles get more weight than others. The final reward can be a single number, but it's informed by the entire critique process rather than a single pass. Then you get to inference time. The magic is that the model doesn't just produce one set of principles and critiques. It samples multiple sets in parallel. One approach is majority voting on the best critiques. Another approach uses a separate meta-reward model, meta-RM, to evaluate all those critiques. That meta model can weigh them and produce a more nuanced final reward, maybe something like 7 out of 10. The paper also talks about sampling principles dynamically, based on the query and candidate responses. This lets the model adapt on the fly. The result is a flexible, context-aware reward system that's not tied to a single, static rubric. All in all, SPCT turns the model into its own grader, generating both the criteria and the critiques, then merging them in a thoughtful way. That's why it scales so well when we ramp up inference-time compute. Now let's look at how these models determine what's correct and how we teach them to do it. The paper first defines a rule for correctness. If you have multiple answers, the one with the highest predicted score should match the actual best answer. If there's only a single answer, the predicted score should align with the ground truth. That sets the training target. However, pre-trained models can be unreliable if you just ask them to critique without guidance. So the authors introduce hinted sampling. This encourages the model to produce critiques in the right format by aligning them with known truths. It's like giving the model a gentle push so it doesn't take shortcuts. Then comes the second component of SPCT, rule-based RL. This fine-tunes the model through a structured pipeline. The model samples its own principles and critiques, checks how close they are to human-provided truths, and gets rewarded for accurate evaluations. There's no fancy, hand-engineered format reward. It's simply about being correct. Finally, we see how the model scales at inference. It samples multiple principal critique pairs for each answer, then aggregates them into a single reward. That's the inference-time scaling part. More principles mean more diverse viewpoints. If some are off base, others might correct them, especially when a meta-reward model steps in to judge the judges. That's the essence of SPCT. From principal generation to robust inference, with built-in safeguards to avoid shallow or repetitive critiques. Now let's check out some actual numbers. The paper has a table 2, that compares various reward models on multiple metrics. They look at something called reward bench for overall reward modeling, PPE preference and PPE correctness for preference alignment and factual accuracy, and RMB, real mistake benchmark, for spotting obvious reasoning errors. If you scan table 2, you'll see that public models like Skywork do well on raw accuracy, while GPT-4o leads in broader metrics. But DeepSeek steps up significantly when it applies inference-time scaling. Even though DeepSeek-GRM27B lags behind top models when using standard reinforcement tuning, it pulls ahead once it samples multiple responses and uses a meta-reward model to interpret them. Its meta-RM variant hits an overall score of 72.8, edging out GPT-4o and others. This is the paper's main claim. Adding more samples and critiques at inference yields dramatic performance gains. The meta approach also helps weigh the critiques in a smarter way. The bottom portion of the page starts discussing how the benchmarks themselves are set up, mentioning they shuffle decisions to ensure fairness. So the message? You can beat or match even bigger models if you exploit inference-time compute effectively. That's a significant finding for anyone who wants to get top results without always training colossal models. Next up, how do different pieces of this method contribute to the overall success? This is where tables 3 and 4 come in. Look at table 3. It shows the model's performance as we increase the number of inference-time samples. With just one sample, DeepSeek-GRM27B sits in the middle of the pack. But sampling 8 responses and voting on them makes things better. Bump it to 32 samples, and DeepSeek-GRM27B plus meta-RM climbs to an overall score of 72.8. That's the top result. Then check table 4, the ablation study. This one asks, what if we remove certain parts? For instance, if you remove principal generation, performance dips. If you skip reinforcement learning, it drops too. Even hinted sampling is important for helping the model adhere to the right critique format. One interesting detail is that cold start pre-training helps but isn't absolutely mandatory. Even without it, rule-based RL elevates the performance. We also see that how aggressively you filter with the meta-reward model matters. If you're too strict, you might discard decent critiques. If you're too lax, you might let bad ones in. There's a sweet spot. The main takeaway: SPCT is a whole ecosystem, and each component principles, hinted sampling, RL, meta-modeling, plays a role in achieving strong, generalist performance. Finally, let's bring it all together with some visuals. Look at figure 4 here on the left. It illustrates inference-time scaling. As you increase the number of samples per answer from 1 to 32, the model's accuracy on reward bench steadily goes up. DeepSeek-GRM27B with meta-RM rises above simpler baselines and even edges out the smaller 16B version of the same model. Now glance at the right side. That graph focuses on training time scaling, just making the model bigger. Naturally, bigger variants like DeepSeek-V3 achieve high accuracy if you decode them with a greedy strategy. But an insightful comparison is that DeepSeek-GRM27B, when it uses inference-time scaling, matches the performance of a much larger 671B parameter model. That's huge news if you're worried about compute costs. They also mention how principal generation remains essential, no matter the size or decoding method. In some cases, just upgrading your model size or prompts doesn't automatically deliver better generalist reward modeling. When they tested with fewer instructions, they saw a dip in performance, reinforcing the idea that robust principal generation matters. So that's the core message. Inference time scaling, with techniques like SPCT and a meta-reward model, can rival simply building a bigger model. It's a more efficient, adaptable approach that can significantly boost performance without requiring a massive training run. Thanks for joining us today. Happy exploring!